Okay. Well, first, find a solution by substitution. Pay attention if you didn't know how to do the solution by substitution, okay? So, substitution. Okay, solve. One equation for x or y. Okay. Now, which equation is going to be the easiest one to solve for x or y? The first one or the second one? Indicate with your finger. Second. Okay. Which variable in the second would it be easiest to solve for? X or y? First or second variable? Yeah. It's really easy to solve this for y, right? Now, if we had to solve this for y, it wouldn't be bad, but we'd have fractions. We'll go as long as possible. Okay. Through the second equation and solve for y. We get, let's just say it's 2x plus y equals 11, okay? Then 3 dots, you want to show the steps. If you want to reinforce them, so you don't want to lose track of them. But show the steps, you get y equals 11 minus 2x, and it's pretty obvious. You subtract 2x from both sides. You don't move the 2x over there. You subtract 2x from both sides. It's fine to think, well, I'm going to move this over there. It's going to be negative. Now, why is it going to be negative? It's going to be negative because I'm subtracting it from both sides, and that's what it gives me. Okay. You know, cancellation. It looks like I ought to be able to cross these two numbers out because they're the same. Okay, is there a reason for that? Can you justify that using the rules? You may have rules for cancellation, or you might just use the basic rules of algebra, okay? But just because it looks like you ought to be able to do it doesn't mean you're going to be able that it's valid. So you got to be careful about doing things because of the way they look. Keep in mind that because it always leads to problems if you don't think in terms of the rules. Okay, so anyhow, we got this. Now, we substitute that into the first equation, right? We get 4x minus 3 times y, but now y is equal to 11 minus 2x equals g. Let's say that's 19. Okay. And now that's an easy equation to solve for x. No fractions. And if it did have a fraction, what would you do? You'd multiply by a common denominator so you don't have to work with the fractions. Okay. Not because you can't work with fractions, hopefully you can, but because you're much less likely to make a mistake if you're not working with fractions. There are more steps in working with fractions. So that's something you always want to remember. If you'd have solved this one for y, you'd have ended up with denominator 3. Multiply everything by 3, denominators go away, smooths out, and it's easy to solve. Well, here we go. So that's 4x minus 33 plus 6x equals 19, which is 10x minus 33 equals 19. So a couple of dots here because we want to fill in the steps. That gives us 10x equals 52. Okay. Couple of dots, x equals 52 over 10, which is 26 over 5. I would say avoid the temptation to use your calculator to find a decimal. Not although you wouldn't need a calculator here. It'd be okay in this case because you're sure you're getting an exact result. But if you put 26 over 17 into your calculator, you're going to get a big long decimal number, you're gonna have to round it off or truncate it or do something. It's not gonna be exact. We want the fractions. I'm gonna work in terms of fractions. So we get x equals this. And now, I didn't leave myself enough room, but we substitute this back into one of the equations. Or if you want, substitute it back into here. Now you're at risk when you do that, because if you didn't solve this equation correctly, this is going to give you an answer that seems to make sense. Okay? But if this is solved wrong, of course, if this is solved wrong, this is wrong anyway. Okay? So it's fine. Okay, go ahead and substitute back here because it's easier. But then, in general, you want to plug it back into one of your equations to see if it works out. Then you're sure you have the right solution. Well, you plug this in here, and it gives you y equals 11 minus 2x. Okay. And 11 is 55 fifths, and 2x is 52 fifths. So that gives you y equals 3/5. Now, I'm not 100% sure of that. I never trust my arithmetic when I do steps in my head. Of course, it's been years since I made a mistake with mental arithmetic and admitted it. Okay, well, no. You see me make mistakes all the time, okay? And you're going to make mistakes. So I don't mind making a few mistakes, because especially if we're going to check them. Okay, so we plug these back in. We check that in the first equation, we get 4 times 26 fifths minus 3 times fifths equals 19. I think I had to use the 19, didn't I? I never did write down what my numbers were, but there's the 19, so it's implicit. But, yeah. So the equations ought to be 4x minus 3y equals 19, 2x plus y equals 11. That's what I was solving. I didn't write them down. I was worried about space and just neglected to do that. Anyhow, I multiply through by 5. And you can do that. You're going to get 104 minus 9 equals 95. And that checks. Okay. Another way to check and see if your solution is at least plausible is you plot these two equations. Now, what I said to do, if you don't know how to do this by substitution, okay, for some of you didn't, graph it. Well, that's something we had last week. If you don't know at this point how to graph it, make sure you try to get that. Okay. But the intercepts, okay, the equations are, I better write out my equations here. Okay, they're my equations. If x is 0, I get negative 3y equals 19, right? So the intercepts are going to be, well, divide 19 by negative 3. Writing this pretty small. something you really not need to know how to do. But I let x equals 0 so that y is negative 19. Well, negative 3y is 19, so y is negative 19 thirds. And what you have to understand is I let x equals 0, and that gave me y equals negative 19 thirds. Okay? Written a little small. And negative 19 thirds is a little less than negative 6. And then if I let y equals 0, that's going to give me second coordinate 0. First coordinate is 19 fourths. You might not be able to read that, but there it is. Well, 19 thirds is about negative 6, right? Pretty close to negative 6. So I know that I'm going to want to have like negative 8 here, which I can easily subdivide and give me negative 4, negative 2, and negative 6. So negative 19 thirds will be just a third more than negative 6. That's actually a little high, but be around there, okay? And then 19 fourths is just a little less than 5, right? So I'll take a risk. I'll say, okay, I think we're probably going to be okay having 8 out here, which will give me 4 here, 2 here, 6 here, and 4 3/4. Well, here's 4, here's 6, so here's 5. Negative 4 3/4 would be about here. So those are my two intercepts. So here's my line. Y equals 4x minus 3y. That's not what it equals. It equals 19. 4x minus 3y is 19. And then 2x plus y equals 11. If x is 0, y is 11. Well, 8 is here. There's 4, there's 2. And 4 is about this much, so 12 would be up about here. So 11 would be about here. So this is the point. First of all, let me label these points. Go back here. Here's 0, negative 19 thirds. Here's 19 fourths, 0. And then my intercepts here are 0, 11, and 11 halves, 0. And so here's my 0, 11. And then 11 halves is 5 1/2. Well, this is a little less than 5. 5 1/2 is about here. Okay, so this is 11 halves 0 about here. And now you come through here, and my intercept, my graph makes a certain amount of sense. We see that x is probably a little more than 5. Well, 26/5 is 5 1/5, right? That'd be 5.2, okay? And y is down here. So the y coordinate, this graph actually turned out pretty well. If this is 2, then here's 1. And the y-intercept is a little less than 1. Well, 3/5 is a little less than 1, right? So in all these ways, I gain understanding of this system of equations. Okay? So we do all that. Now, before I get to the line perpendicular, the first line through the point of intersection, of course, that was due today. The line is going to have negative reciprocal slope. Okay? Review what we said last time in class if you need to, or get into the open math and make sure you understand what they're telling you. Same thing I told you. And let me just put another little plug in. It's been 5 days since we had class. You really need to think about going to the videos and spend 5 or 10 minutes clicking through them to remind yourself of what you saw. That keeps what you remember about the class fresh. Not only that, it gives you a little more perspective. It reinforces those neural circuits. And you're going to save yourself time. You spend 10 minutes, you can save yourself an hour because you're going to understand it better. Not only that, but since you understand it better, you're going to be able to perform better. It's more likely to be there when you need it on a test. Okay? Right through the video. Okay? Doesn't necessarily have to be the videos made in class. If you the videos that you think serve better, okay, but in class we cover a lot of topics. In Open Math, they cover the same topics, maybe a little different language, and I don't like their interface, the whole thing. I don't like the way most of those videos are made, but you might. Okay, it's different. Same stuff. It's just that you see writing go up on a whiteboard or whatever, instead of see somebody actually doing it. I think that, I go with the philosophy, I'm going to do something different than what they do. You're going to see me doing it. It might be hard to watch, but okay, that's all right. So, yeah, do what works for you, but do something. And this means if you prefer to click through the Open Math videos, that's okay too. Click through the darn things quickly. Spend 10, 15 minutes looking at the basic videos. Reinforces it. Then, if you got to come back 2 or 3 days later, like at the last minute, which is when most people get stuff done, it's not a good idea. Okay? You don't learn as well, but I did it when I was a student too. You're under pressure from all kinds of directions, so you do what's necessary. And it wasn't really necessary, but I couldn't convince myself to do what I knew I should have done, and maybe you can't either. No excuse for not trying. I'd have been better off if I had, and you would too. Okay. Anyhow, how you want to approach it? Okay, well, whatever. Don't sit around for 4 days until the thing is due and then try to reconstruct what you kind of understood from class before. Reinforce it. Okay. Now, back to the actual problem. I was going to go ahead. Now I'm going to go ahead and anticipate what's due for next time. And let me just double check. Make sure I'm telling you the truth about what's due for next time. I hate to lie, but I do make mistakes. So. Yeah. 2 things due for next time. One is solve the system by elimination, which is kind of easier than substitution. Okay. And it's really what you use for linear equations. That's what I was going to do, and that's the right thing to do. And you've also got properties of exponents. You might not be able to talk about that during class if you have to spend too much time on this. But it's something that you should pretty much know, and you should be able to learn from the Open Math videos. Okay? And if I find you can't, that's what we'll talk about next time. Well, so let's write out our equations again. Okay, there's my system. Now, notice, if I multiply both sides of the second equation by 3, then I'm going to get a 3y here. Then if I add the 2 equations, I've got a negative 3y here and a y here. Y goes away. And I end up with just an equation for x. It's a slicker way than substitution. Now, substitution is important because if the equations aren't linear, if you got an x squared there or 3 over y or something like that, it's not, this isn't going to work. Elimination isn't going to work. You have to use substitution, which is why we learn it. But when you have linear equations, which is what we have here, this is kind of slick. So I'm going to rewrite my system. I'm going to put a circle around 1, which means I'm just going to write down equation 1. Then I'm going to write down 3 times 2 with a circle around it. The 1 with a circle around it I use to designate equation 1. A 2 with a circle around it is equation 2. I'm going to multiply both sides of that. When I say 3 times equation 2, I mean multiply both sides, which means I multiply every term by 3. And I get 6x plus 3y equals 33. Then well, now equation 2 is this one. Equation 1 is what it's always been. So when I say 1 plus 2, I mean go back to my last 2 equations and add them. Well, 4x and 6x gives me 10x. Negative 3y and y is 0, and I get 52 here. Okay. So x equals, again, 26 fifths. 52 over 10 is 26 over 5. Okay. Now, what we did last time, and it's perfectly permissible, we plugged that result into this equation that we got when we eliminated one of the variables, okay? Well, when we solve for what? Solve one equation for what? We're not going to bother solving an equation for y. We're just going to plug this into either one of these equations and get y. Now, I'm going to choose this equation because we just got plain old y. It's going to save us a step. If I'd have used this one, I would have gotten the same result. X equals 26 here. I'm going to plug that in here, which gives me the equation 2 times 26 fifths plus y equals 11. Multiply both sides by 5. And I'll actually do multiplication by 5. 5 times 2 times 26 fifths plus 5y equals 55. Just to review how this works out. Your numerator would be 5 times 2 times 26. Your denominator would be 5. So I can write that as 5 over 5 multiplied by 2 times 26. Then my 5 divided by 5 is multiplied by 52. So I've got okay. So I've got this. I'll put some dots here. Well, that agrees with our previous solution, right? So the way you solve by elimination is you match up either the x's or the y's. Now, sometimes I wanted the, if this had been 7y here, and I wanted to match them up, well, I'd multiply this by 7 and multiply this by 3, and it would match up. I'm not going to do that. Open Math will show you how to do it. The principle is you match these up so that you have equal and opposite coefficients on either x or y. Okay. And I might do an example of that, but I do want to talk a little bit about exponents. I don't think I'll have any serious trouble understanding that if I don't go over it today. The principle is you want to eliminate a variable. That's why we call this elimination. It's more efficient than substitution. I'll just put a check mark there because we've already checked that solution, okay? Okay, well, that's solving by elimination. Now, I want to get to this thing about perpendicular lines. First place, are these lines perpendicular? Looks like they might be if my scale's a little bit distorted. But that doesn't really look like a right angle, so we suspect that it's not. We suspect they're not perpendicular. Okay, so color here. What's the slope of this first line? No. And not 2/3 x is greater than 2/3, but I'm going to put my x, put it in x plus b form. Okay, so this line has a slope of 4/3. Just solve for y, that puts it in slope intercept form, and you can read off the slope that's what's in front of x. Okay. And then the second one. Slope is -2. Okay, well. They're perpendicular if and only if, so I'll put that extra F on there. Okay. If and only if the slopes are negative reciprocals. Okay, well, the negative reciprocal of -2, reciprocal is 1/-2, right? And the negative of that is 1/2. Okay. It's not so that the slopes are negative reciprocals. Very easy to test. Reciprocal means you divide 1 by that quantity. If it's a fraction, you just reverse the numerator and the denominator. You should understand why. And then you put a negative sign in front of it. Okay, so these are not perpendicular. They don't have negative reciprocal slopes. Okay, so now we want a line, a line through the point of intersection, perpendicular to the first line. Now, which one's the first? Let's say first one's this one, right? Okay, so I'm going to say just looking at it, but Line through the point of intersection, kind of a little hard to read the end of that word, but make my choices. But I use the symbol for perpendicular, which is kind of like an upside down capital T. Just indicates something perpendicular to something else, right? So make a right angle. Now that should be a familiar notation, but maybe not. Perpendicular to the first equation. Okay. And that means that I should have about a right angle here. Now my scales and everything are fairly good, but if you take my prediction here, it looks like the y-intercept would be a little more than 0.4. I don't know if that's going to be accurate or not. Well, just a little bit, okay. So we want a line through the point of intersection, which is, make sure I've got it right, 26 steps. 3 steps. Abbreviating perpendicular, I'm getting tired of writing all those letters. Perpendicular to line (4x minus 3y equals 19). Slope of the line, as we saw previously. Negative 19/3. Okay. Slope of the perpendicular line. It's not negative 19/3. We just want to write down any old fraction. That's the on board with the denominator of 3 4/3. Not negative. Slope of the perpendicular line. This slope is negative 3/4. So we know a point and a slope. And the reasoning of that is the reasoning we've been through several times and several examples. You know, I really have to set up a monitor that tells me when this happens. You know, I've been writing kind of small on the assumption that this thing was zoomed the way I originally had it. Foolish me. There it is. I think it's in focus. I don't know why the camera does that. Great camera, but it's got some funny little quirks. Okay, anyhow, the line is y equals mx plus b, as we've done previously. M is negative 3/4. And got to go through this point. y equals 3/5, and x equals 26/5. And now what we get ought to kind of match my picture. I just predicted, based on my sketch, that the y-intercept ought to be a little more than 4. I don't believe that for a minute, but yeah, it should at least be somewhere between 2 and 6, maybe. Okay. So I'll commit myself to believing that it's between 2 and 6, so I can be all embarrassed when it's not. Okay. Now, there we have equation of line. Well, there we have what we need. So y equals -3/4 x plus b. That is the slope. -3/4. And furthermore, y equals 3/5 when x equals 26/5. So we have 3/5 is -3/4 times 26/5 plus b. Okay. Now we easily solve for b. We just multiply through by common denominator. What's the common denominator? Well, we don't have enough fingers to show me. It's 4 times 5, which is 20. So I'm going to write that out just real explicitly. The step you might or might not be able to do. And of course, this could be reduced to -39/10. And you only have to multiply by 10. I'm not going to bother. I'm just going to multiply by 20. It's going to be as easy one way as the other. So we multiply by common denominator 20. You get this, which gives us 60. Gives us 3 equals -78 plus 20b. Turns out my estimate is pretty good. Looks like this the y-intercept is going to be 3.9. I estimated 4.1. And I thought I might be closer. I wanted to hedge my bets. I said between 2 and 6. Okay. So we get, actually, never mind. B is -81/20. Is even better than I thought. Plus 81/20. I said 4.1. It's 4.05. Okay. So you should be awestruck by my uncanny accuracy in drawing the graph. Actually, just pure luck with a little bit of skill. Okay. So right there it is. There's 4. Is that y-intercept pretty close to 4.05? Well, I'm not going to gloat because next time I do it, I'll probably have the wrong sign or something. Okay. I want to put that 81/20 in there before I should. -3/4 x plus 81/20. And that does equals, not even an approximation, if you really want decimals, negative 0.75x plus 4.05. That's an equal sign. It's not a wavy equal sign. It's not an approximation. Then we could plug in then 26/5 for x and verify that y would indeed be equal to 3/5. To completely verify that it goes through that intersection point we found in the original two lines. Okay. That's the process. Now, if you know how to do that, it's going to be a significant advantage when you take pre-calculus. Okay. The last thing you do in pre-calculus is simultaneous linear equations. We're doing it now because this is where it comes up in the order assignments we're doing, and it comes naturally out of looking at equations of straight lines. If we wait until the end of the course to do it, you might lose track of equations of straight lines and not see how all this forms just kind of one nice little whole. Okay. Okay, good. Now let's see where we want to go next and see what kind of shape we're in with exponents. Okay, this is kind of important. If I work through this system, if I do the steps, they do it by elimination. Well, if I multiply the first equation by 5, okay, I get a 5y, which would add to the negative 5y would give me 0. Meaning I'd eliminate y. If I can do that. Okay. And then your second equation doesn't need to be multiplied by anything. Sometimes it will. There we have it, right? Now, if I add the 5y and the negative 5y, I get 0. Okay. And then I add negative 15x and 15x, I get 0. Now that's going to be fine if I get 0 over here. Because 0 plus 0 is equal to 0, right? About 45 and 4 isn't going to give me 0. So it's not so fine. It gives me 49. Zero is not equal to 49. No XY pair satisfies both equations. Solution does not exist. It's perfectly possible to have two equations where the solution doesn't exist. Now let's think about why the solution doesn't exist. Why no solution? Well, if I solve these equations for y, I get y equals 3x plus 9. Okay, second equation implies that, well, negative 5y equals negative 15x plus 1. So that y equals 3x minus 4/5. a big deal here is that you got 3x here and 3x here. What does that tell me? That tells me that both lines have the same slope, but they have different y-intercepts. Y-intercepts are 9 and -4/5. Meaning that if you were to graph these, you'd have a line here with a slope of 3. So this is the 0, 9 slope 3. And this one would be 0, -4/5. With a slope of 3. Meaning that these lines are parallel, meaning they never meet, meaning there's never an intersection point, so there's never any set of x and y values that makes them both true. So parallel lines never meet. There's no common point in these graphs. There's no solution. Now, I'm not going to write it out, think about it. If instead of 4 here, I wrote 45, sorry, 9. Okay, no, 45, sorry. If this is 45, then this would be, sorry, I wrote -45 here. This is -45, then I have a -45 here, and I get 0 equals 0. Well, if this is -45, the slope is still 3. -5 into 45 is -9. Yeah, this would be -45. I get the same y-intercept, and both lines would be the same as this one. Okay. Then there would be infinitely many solutions because every point would be a solution. Every x, the coordinates of every point would give me 2 numbers for x and y, a number for x and a number for y that satisfy both equations. Okay. So when you have the system of simultaneous equations and 2 variables, they represent 2 lines. The lines have different slopes, well, then they got to meet someplace. So there's a solution. If they have the same slope, then maybe they meet, in which case they're the same line, infinitely many solutions. And if they don't meet, then there's no solution. Okay. In other words, if they don't have any common point, well, either they have infinitely many common points or they don't have any if they're parallel. Either they never meet or they're the same line. Okay. Didn't say that very well the first time, but sort through it. X squared cubed means multiply x squared by itself 3 times. I multiply x squareds and I have 3 x squareds to multiply. It gives me 6 x's. And of course I can write that out. Okay. Now, there's a very common error people make. When they see the 2 and the 3, they want to add them instead of multiplying. If you know and visualize what x squared cubed means, you're going to know better than to add the exponents. Now, this is confusing because there's another law that says x squared times x cubed. Means what? So that means x times x multiplied by x times x times x. Now, how many x's have I got? 5, right? It's confusing because this is a multiplication. Makes it look like you want to multiply the exponents, but that's not the way exponents work, and you can see that here. You want to always think through how this would be written out. You want to visualize it. If it's x to the 17th to the 200th power, you visualize 17 x's multiplied by each other, and then 200 of those. Okay? You're going to get more than 217. You're going to get 3,400. Okay? So x to the a raised to the b is x to the a times b. X to the a times x to the b equals x to the a plus b. You'll try to memorize these. Although if you've got a really good visual memory, a photographic memory, you probably can. Okay, understand why they're true. Just understand this simple example, and it'll always keep you straight if you think about it, whether you add the exponents or multiply them. Okay, another big deal. Negative exponent means this. Okay. Give you a quick reason for that. And then probably reverse it. Because of this rule, you multiply x with negative 4 by x with 4, you get x to negative 4 plus 4. That equals x to the 0, and x is 0 has to be 1. Okay? Now that's a rule in itself. Any number to the 0 power is 1. That's why this is totally rigorous because you kind of use this to conclude why this is so. And also, if instead of x to the negative 4, I write 1 over x to the 4, well, clearly 1 over x to the 4 times x to the 4 is x to the 4 over x to the 4. And these are the same, so that's 1, right? Okay. So it has to be. So it's actually a choice you make, but don't worry about that. Understand that's what a negative exponent means, and so forth. Okay. Those are the points of major confusion. Now you're going to be looking at some more complicated expressions, but the rules for those expressions are a little easier to keep straight than what I've just shown you here. So really try to be straight on this much, because this is where most of the errors come from when people are dealing with exponents, and those errors are always fatal, almost always fatal, unless you just totally luck out somehow. Okay.